Welcome back. It's a great pleasure to introduce our next speaker, Nelly Ng from the Freie Universität Berlin, who's going to talk about the fundamentally maximum efficiency for quantum heat engine.
Thank you. Thanks for inviting me. It's really great to be part of this conference, and I have been enjoying myself quite a bit. So today I want to talk about quantum heat engines. And throughout this conference, we've seen many things about information theory, resource theories, and how they have provided a kind of new framework for us to describe thermodynamics. And indeed, one can apply this framework and try to study generic models of heat engines and to evaluate what is the theoretical limits on the achievable efficiency. And this is an analysis that I would like to share with you today. So this project is joint work with two people. There's Misha Woods, who is currently in Zurich, and my previous PhD supervisor, Stephanie, who is in Delft. So, a few words on quantum thermodynamics. So we've seen many talks about thermodynamics in this conference, but essentially this is a really very old branch of physics that has evolved a lot throughout time. The most old school version that we've seen was applied to macroscopic systems, where most of the time we are dealing with equilibrium states. So the central concepts surrounding that would be ideal gases, PV diagrams, thermodynamic identities, which would describe variables such as volume, pressure, and so on and so forth. And I found that thermodynamics was a very interesting and useful subject back then, because although the objects themselves can be quite complicated from the mechanics point of view, nevertheless, if you want to use them to build engines, to extract work, for example, then you can efficiently describe them with certain macroscopic variables. And this is because of the bulk properties of systems, such that statistics really becomes a very powerful tool in singling out the average behavior of a system. So of course, thermodynamics also started out more, most of the laws were started out in a more phenomenological kind of expression, and later on they had more quantitative versions, and they were grounded more in the development of statistical physics. We've seen refinements of thermodynamics when we enter the so-called mesoscopic regime, where we're still looking at systems which are effectively classical, but they are really small and subjected to fluctuations. For example, if we think about the physics of protein folding, one of the core essences is that this is a process where a state which is non-equilibrium initially interacts with a thermal bath and evolves towards equilibrium. In the cell environment, you have molecular motors that function to transport materials in and out of the system. And people start to wonder whether thermodynamics can be kind of refined in order to describe certain properties of such systems. And indeed, the description of thermal has become very different in this light. So one example, of course, is work extraction, where previously in classical thermodynamics, you have a much more clear-cut separation between work and heat, work being extremely ordered energy which can be stored, heat being something which is irreversibly dissipated. But as more of the mesoscopic thermodynamics evolve, non-equilibrium behavior becomes really important, and work extraction itself is associated with stochastic processes, and then people start to view work as a random variable by itself associated to these processes. Now, many models of system-bath interaction have been studied, and we also see that refinements of the second law by talking about what fluctuations do to have probabilistic versions of second laws also come into picture. and there's been a lot of discussion for the past few days on these topics as well. So currently, the systems that we play with in the lab are not only very small, but also quantum mechanical in nature. And this defines the kind of essence of quantum thermodynamics, where the systems, the quantum features of the systems become really very prominent. And this is the goal of quantum thermodynamics, I would say, is to say that we start out from the basic principles of, or the basic framework of quantum theory, and then we look at, sometimes we use tools from quantum information theory, and the goal is to revisit some of the statements that classical thermodynamics has made. Here I have some key features which would maybe highlight the differences that quantum systems bring towards thermodynamics. So first of all, we see that the systems that we deal with are really very small. And for example, we can have in quantum thermodynamics heat baths which are really finite dimensional. Whereas in classical thermodynamics, a bath is usually something which is infinite in energy and continuous in energy spectrum, and its temperature never changes even after many interactions with different systems. In quantum thermo, it's not really the case anymore because the interactions sometimes happen on a more local scales. Universally in quantum thermo, you would have machines which are really small, and maybe just a few qubits, whereas in macroscopic thermodynamics, you would have a piston with ideal gas. And I will come back to this later, but we see already in mesoscopic thermodynamics that the separation between work and heat is not so clear anymore, and this becomes more pronounced also in quantum thermo. And finally, you have special quantum effects, which are, for example, coherences that build up between energy levels. And also you can create entanglement between systems, but it's not clear how do these in general affect the efficiency of quantum heat engines. Excuse me. So even as I am a theoretical physics person, I would sometimes like to, when talking about thermodynamics, keep in mind certain concrete pictures of what the experimentalists think about when they say quantum thermal machines. So here I'm giving just a few examples so that we can all see what the experimentalists are interested in dealing with. So this is actually a theoretical proposal for a quantum refrigerator, and it proposes the design of a finite-sized machine, namely 4 quantum dots, each containing, say, a single electron. And each of these dots are then coupled to different thermal reservoirs which have different temperatures. And the interaction Hamiltonian between these 4 dots can be designed such that after one cycle of the heat engine, or the refrigerator, a 4th dot gets cooled down. So cooling is quite important in a sense that, at least in the context of quantum computation, where the initialization of states with very high precision is a popular demand, basically. So this is one of the heat engines that experimentalists could be interested in. And the second example would be this, which is a calcium ion, a single calcium ion, which is trapped within an ion trap. And it interacts with laser beams and electric noise, which serves as thermal baths. And one can use this tiny heat engine in order to extract work, store it, and later demonstrate the usability of this energy in, say, fueling mechanical motion of a particular atom. So hopefully that gives some concrete examples of what thermal machines look like. These are some of the big questions in the field of quantum thermal, and I think they can be safely summarized into these 4 categories. The first one is to talk about what are the conditions and mechanisms for quantum state to equilibrate towards the canonical ensemble. And the second one would be looking at the energy cost or work cost of certain computations or information processing. The third one would be to look at coherences and entanglement and say something about the generic role of these effects when we are dealing with thermal machines. And the fourth one, which is the mainly focus today, would be quantum thermal machines and the usefulness of such things. So there are, of course, still various answers in terms of what is a useful quantum thermal machine. There's refrigeration, there is even thermometry, making very precise measurements of temperature. But today we're just going to focus on heat engines, which is the problem of, well, how well can I extract and store good quality work? So, what are heat engines? First of all, we know that if we start off from a single heat bath, then we cannot extract any work at all, because you cannot convert heat to work without inputting any kind of resource by itself. However, if we have a second bath, which has a different temperature, then one can make use of this kind of temperature difference in order to extract work, typically by using a particular machine. And this machine can interact with both baths, goes through a cyclic process, and at the end outputs some ordered form of energy. The efficiency is then defined as a ratio of 2 quantities, the amount of work extracted, and the second one would be the amount of heat that comes out of the hot bath. Now, I think that heat engines play a very historical, important role in motivating the study of thermodynamics, because people probably wouldn't have cared so much about constructing this whole theory if they did not want to make engines and design them so that they would have high efficiencies. And this is why Carnot's work was quite important during his time, because he reasoned that if you have 2 baths of different temperatures, then there's, irrespective of the details of the bath, there's always a protocol in order to extract work at a particular maximum attainable efficiency, which is what we know now as the Carnot efficiency. And this efficiency depends only on the temperatures of the bath. Now, of course, efficiency is not everything when it comes to heat engines, because we also, for example, want to study the power of a heat engine. And in light of that, most heat engines which would attain Carnot efficiency would be really slow and infinitely slow. So maybe this is not very practical, but for today, let's just worry about the fundamental aspects of what can be achieved and what cannot. So our goal today is to apply the resource theory framework in order to construct a generic model of quantum heat engines, and we want to see what can we learn from such a perspective. Before that, let me again address this problem of defining work in more detail. As I've said already, there's not a consensus, even among the community of quantum thermodynamics, as to how work should clearly be defined. And if you think about this, the reason is quite simple. By extracting work, usually we mean that we store it in a particular physical system. So if you think about what work extraction in classical thermodynamics is, it's that, well, I have something like a battery. A usual battery that people would see is some weight hanging on a rope. And extracting work would mean that I raise this weight up to some height and I store potential energy in this height difference. Now, of course, there are thermal fluctuations that would affect the state of this weight. That's obvious. But the point is that the energy scale that we store here is much larger compared to the fluctuation, the thermal fluctuations. And so at least by physicist standards, this amount of thermal fluctuation is infinitesimal. So it's also very straightforward to kind of get the amount of work back out from this process by lowering this weight. You have this exact same amount of energy. However, this is radically different if you were to consider storing work in a quantum mechanical system, because most of these systems have energy scales which are very small. And the amount of work that you store by putting into the system is actually quite comparable to the thermal fluctuations that the battery is experiencing. And therefore, there's not so much of a clear-cut difference between heat and work anymore when you think about it operationally. So this has led to a kind of wide range of different quantifications when people talk about extracting work in the quantum regime. So I was speaking about this yesterday over dinner, and someone asked me this question about how one should define work. And the answer that I gave is that if you take 10 people from the quantum thermal community, they'll probably come up with 11 different definitions of work that should sound reasonable, and maybe everyone will take a different one. That's a scenario that is unfortunately still present, and I suspect will continue for some time. But indeed, we can acknowledge that there are different definitions and work with some of them. So I'm going to give a slight overview on some of the different perspectives. So if we come from a more information theory perspective, then we are going to be interested in extracting what we call single-shot work. So usually this would involve statements like, after one cycle, a single cycle of this protocol, I want to extract as much energy, at least that much energy, maybe except with some probability of failure, epsilon. So these are the usual statements. Now, also, people have tried to look at the change in average energy, but try to separate out the contributions from work and heat by saying, let's attribute the changes of Hamiltonian to be as quantified as work, and the rest as heat. So this is quite actually a popular way to do it. But if you think about resource theories where the Hamiltonian is time independent, then one might see that it's maybe not so easy to follow this line of thought. There are some works which look at a more kind of axiomatic approach in defining work, namely that you start off from a set of principles on how you expect a work quantifier should behave, and you look at what are the quantities of a system that would satisfy such a set of principles that you want. So most of the time, as I mentioned, you would quantify work by stating an explicit battery model and the initial and final states that you achieve, and look at that that amount of energy difference. And in resource theories, usually what people do is also to fix the initial and final states that you desire, and then you ask, well, can I achieve this transition or not? So one very straightforward example that is popular in resource theories is to use a two-level system to store work. You can think about starting off in the ground state of the system, and then after the protocol, you require that you have extracted work by exciting the system to the first excited state. And you ask, well, can this transition occur or not via, say, thermal operations? You can use many different kind of battery models. For example, the two-dimensional qubit. You can use harmonic oscillators. You can even use a system which is fully degenerate in energy. So you are basically storing purity as a resource, and then later using things like Landauer's principle to convert it back to energy while thermalizing with some bars. So So far, so good. And lastly, I want to really say that most of the heat engine analysis up to date, where you look at specific protocols in the quantum regime, they would quantify work by looking at the average energy increase in the battery, maybe plus some additional statements on how the higher order moments of the energy distribution looks like. Why? Because it's relatively simple to do that. So, how should we define work? In this comic strip, you see that the supervisor and the student actually don't agree on the definition of working hours. So you can see how this might be a problem, right? But this is actually the same thing in thermodynamics, because when you have so many case-by-case analysis of specific heat engines, and everyone is not agreeing on the definition of work, you cannot compare these analyses. You can't say which is better than the other, so on and so forth. So I hope that after this talk, there will be a maybe clearer guideline to how one can characterize different qualities of work. But let's move on for now. So let's briefly recap some of the things in resource theories. So as we've seen, a resource theory usually is specified by the free operations, free states, and then the possible state transitions that arise out of this framework, where the state transition conditions are usually phrased as monotones. And one of the fundamental paradigms in resource theory thermodynamics would be thermal operations. And the state transition conditions for that would be thermal majorization, and that's basically the zonotopes that Rob was talking about a few days ago. So these state transition conditions are only necessary in general. However, if you have states which are time translation invariant, then they also become sufficient. So maybe just two quick things to notice and recall about these thermal operations, namely that you see that in that diagram you have one of the straight lines, and this is actually the thermal majorization curve of a particular state, the Gibbs state of the system, that takes on already the temperature of the bath that it interacts with. So this tells us actually that all initial states of the system can go to this Gibbs state via thermal operations, and also that this Gibbs state is going to be invariant under thermal operations. And the second thing that we want to recall is that thermal operations would give you a partial order on the states instead of a total order. For example, if you think about classical thermodynamics, the second law, when applied to a system that undergoes heat exchange with a bath, you would say that the second law would say that the free energy would decrease in this process, but it doesn't say anything more. However, if we take the free energy to be the unique kind of monotone, then this would apply a total order on the set of states, which does not happen in thermal operations. So one of the questions that people ask is, why is there this difference, this gap in the structure? And of course, there have been many answers to this, but I think the general format of the answers is that thermal operations is still too fundamental and different from what we observe in classical thermal, and therefore there must be some further generalizations in particular limits that would bring thermal majorization to connect with free energy. So one of these extensions that people have looked at are catalytic thermal operations, where it's basically thermal operations with the additional leeway that you are allowed to borrow a catalyst. This can be any finite dimensional quantum state along with its Hamiltonian, and you're allowed to take this state and use it in your process only under one condition, namely that you return it exactly back as it was. So I guess that maybe to quickly motivate why people look at catalysis at the first place, I think in part the reason was to kind of bridge resource theories with the description of time-dependent Hamiltonians. Because if you think about, for example, if you go to an experimenter and you say, okay, I want to implement this particular energy-preserving unitary, then what they will tell you is that they have a switch in the lab, they switch it on, it turns on some interaction Hamiltonian for some time, and then you switch it off again. So there are some more things that come into the process of actually implementing this energy-preserving unitary. You can think of, for example, a clock such that it will tell you the time that you should turn the interaction on and then off again. You can think of the whole experimental apparatus actually as a quantum state that participates in the process. So this is partly the reason for looking at catalysts.
Can I just ask a quick question?
Yeah.
When you say the state of the catalyst is preserved, does that mean that I have to return the Marx field has to be what it was? Can I leave it correlated with other things?
I'm getting to that next.
Sorry.
So there are, of course, different forms of catalysis, and I guess the strictest form would be basically what Wayne mentioned, which is exact catalysis, where you have actually no correlations. After you trace out the hot bars, you're required to have no correlations with the system itself. So, question, why do we need to assume that the catalyst should be decoupled at the end of the process? So indeed, I will leave it to Marcus to later motivate a complementary view where you can maybe allow some correlations to exist between the catalyst and the system. But maybe let me just make a few points about this, the reason why people would maybe want to look at exact catalysis. So for one reason, is that the catalyst itself, if you think that you had kind of borrowed this catalyst from a third party, and you use it to perform your reaction. But this catalyst could be part of a larger system where the third party actually holds a reference which is initially correlated with your catalyst. So when you finish whatever you need, and then you need to return this catalyst back to this third party, then building up correlations between the catalyst and the system would potentially sever the correlations that initially the third party had between the catalyst and some reference system. This is one reason. Now, a second reason is that if you look at this condition, it's actually not as strict as it seems, because throughout the process of implementing this energy-preserving unitary, the catalyst can, of course, be correlated with the system and the bars and everything else. So the only restriction here is that once you throw away and forget about the background reservoir that you use in the process, essentially, if you start off with a fresh bath, then the states are effectively decoupled. And throwing away a bath and taking a fresh one is, by assumption, easy to do in resource theories. But if you have allowed final correlations to build up even after you have thrown the bath away, then in order for the catalyst to kind of make a same reaction, you have to start off with a fresh copy of the bath. You also have to start off with a fresh copy of the system. This is another reason. So, of course, one can also easily find necessary conditions, however insufficient, for exact catalysis to occur. And these are phrased in terms of what we call generalized free energies. And these are all basically monotones of catalytic thermal operations. So one can find these necessary conditions by noting that they are basically instances of data processing inequalities, which Rob also had mentioned in his talk. The one thing to note is also that if you look at this whole family of generalized free energies, then the quantity where you take the limit alpha going to 1 would produce the Helmholtz free energy. So the standard free energy is one instance of this whole continuous family of generalized free energies. So, of course, these are necessary but insufficient conditions. However, when if you are looking again at initial stage which are already time translation invariant, then they are also sufficient conditions. And I guess now it's a good time to kind of see the relation between 3 types of different state transition conditions. Thermomajorization being the most stringent one, standard free energy being, well, maybe a bit more lenient, but generalized free energies would be in between them in terms of stringentness. We know that allowing catalysts would give you, would reduce thermomajorization to generalized free energies. And in fact, there's also quite a reasonable way to see how generalized free energies reduce to the standard free energy. For example, this is only one of the many ways. For example, if you take n identical copies of your systems, and you also require, you also only demand that you reach the final state, epsilon close in terms of trace distance, then one can also show that in this limit where n goes to infinity, all the generalized free energy collapse back to the standard free energy condition. So I've been talking a lot about exact catalysis because I work most with them. But there are, of course, other types of catalysis. So the second type would be what Marcus will tell you about, where the catalyst is preserved, but it's only on the marginals, but there can be correlations with the system and the bus. I also want to mention a bit in passing a kind of relaxation on the catalyst, which is also quite interesting, at least from my perspective. These are called inexact catalysis, where I maybe allow you some small errors in terms of trace distance on the final state of the catalyst. So it's not returned exactly, but it's returned epsilon close. Initially, people thought that, well, maybe this is not a very unreasonable requirement, because after all, we know that the trace distance has quite a operational interpretation in terms of how well you can distinguish 2 states. However, it's been shown that if you have no other restrictions on, for example, the dimension or the energy of your catalyst, then inexact catalysis will give you basically no state transition conditions. Any state would be able to be transformed to any other state. And this is in what we call embezzling in thermodynamics, because if you so the essence is that your catalyst can be chosen to be huge, some big reservoir of energy, where you only steal a tiny amount of energy out of it to enable your state transformation. However, because of the size of, basically the size of the system, would allow you to kind of still find that the initial state and the final state of the catalyst is very indistinguishable. So this is the case. So in the heat engine analysis, we will be focusing on the case of exact catalysis. So now let's ask the question of how we would apply all of these things that we know from resource theories in order to build and study a framework for heat engines. So we have 2 bars. And in order to use the resource theory, then we choose one of the bars to be the background reservoir that people use in resource theories. Here I've chosen the hot bars, but in principle you can kind of reverse the roles of the bars and perform a similar analysis. This also means that because in resource theories you allow you basically have no restrictions on the background reservoir that you use, except for that it has to be at a fixed temperature. So there are no restrictions on what the hot bath Hamiltonian would look like. So now I take in the second bath, which is a cold bath, and this is athermal with respect to my hot bath, so I can treat it as a system of interest where I extract work from. So to do so, I attach a battery to the whole system, and note that you could, in principle, allow an engine, and this engine doesn't act as an energy source or sink. It just participates in the process, and then later is returned in its original state. So this would be the catalyst in our picture. Now, all the players are in. We take these systems and we apply an energy-preserving unitary across the global system. We trace out the hotbars. And we want to achieve the final goal where the final state of the battery has some energy increase. That's going to depend again how we quantify this work. So the question is then, given some initial state of the cold bath, well, what is the highest achievable efficiency such that work is extracted and stored in the battery? So before we go on, let's just quickly look at the assumptions of the setup. The initial state of all separate systems are assumed to be uncorrelated. We assume exact catalysis. There can be correlations between the cold bath and the work, the battery in principle. However, in the analysis, we also show that maximum efficiency can always be obtained when these are of tensor product. So this greatly simplifies the analysis because then the terms that come in the battery can actually be factored out. And the rest are just assumptions that come along with the part and parcel of the resource theory framework. So how do we quantify work? Now, obviously, I would be interested in quantifying single-shot work. And to do so, in particular, I use a battery Hamiltonian, which is a quasi-continuum. That just essentially means that there are many, this is discrete, but I can choose the energy levels however I want to, in order to extract the optimal amount of work. So extracting work would then mean having this battery Hamiltonian, fixing an initial and final state that I desire, and then asking if I can actually perform this transition. So we first look at a notion of what we call perfect work. We can take it very literally, meaning that I start off my battery in an initial state, which is a pure energy eigenstate, and at the end I require it to reach a higher pure energy eigenstate. This is perfect work. Of course, we can define also this more generally, namely that we succeed in extracting energy, but with zero increase in the entropy of the battery. So for example, you can also have some spread across energy levels, but this spread, for this whole spread, the energy distribution is basically moved up, and there's no entropy increase in the battery. So later we will look at other types of work where this constraint is relaxed, but let's work with it for now. So the question is then, when is this transition possible? And this would correspond to looking at the system, which is the cold bath and the battery as a whole, and seeing what are the conditions for in order for this state transition to occur via catalytic thermal operations. Now, if we step back and think a bit about what classical thermodynamics would tell us, is that the free energy is the relevant quantity in telling us whether this transition can happen or not. So this free energy has to be non-increasing. However, if you look at the generalized free energies, then because this is a catalytic thermal operation, then all of the generalized free energies would also come into play, and all of them would have to be non-increasing in the process. So the question is whether these additional free energies would affect the maximum efficiency that such a heat engine would be able to achieve. So we're going a bit slow, but bear with me for a moment. And let's ask the question, how well would this heat engine perform if only the free energy matters? So we are taking the constraint of standard free energy should be non-increasing, and we also require the extraction of perfect work. And then the second law would tell us, the macroscopic thermal free energy would tell us that the maximum work that you can extract in this process is going to be given by the free energy difference between the initial and the final states of the cold bath. Now, however, we don't want to maximize work. We want to maximize efficiency. So there's another quantity that we have to take into account, which is this heat flow that comes out from the hot bath. By energy conservation, we can write this in terms of two quantities, the extracted work and also the change in mean energy of the cold bath. And that is very nice because you can then write the efficiency of such a transformation solely in terms of the final, the state of the cold bath. And then to maximize efficiency, you would maximize over all possible states of the final cold bath. So by trying to maximize this quantity, we find that, of course, the Carnot efficiency is going to be an upper bound to the efficiency that you can achieve. No surprise. And this also is true independent of what the cold bath Hamiltonian is, if we look at the standard free energy. And one thing to note is that this Carnot efficiency can be achieved in what we call the quasistatic limit. Of course, this is going to be a very different definition from the historical way that people have described quasistatic, given this resource theory kind of framework. This is a technical definition in our analysis. It means that the final state of the cold bath also has a well-defined temperature, and we are taking the limit where this final temperature is actually very close to the initial temperature of the cold bath. So let me quickly sketch the proof for this, because it will be important to kind of get some insight into the significance of this quasistatic limit. So what happens here is that, well, since we need to optimize the quantity, which is the ratio of delta C over work, let's do this. We fix an amount of delta C, which is the energy change between the initial and cold bath, initial and final states of the cold bath, and then we ask for a fixed amount of delta C, what is the maximum amount of work that one can extract? So in this diagram that you see, the contours would represent a fixed delta C, and what we find is that the work that the maximum amount of work would be achieved when the final state of the cold bath has a well-defined temperature. Now, when we look at if we look at states that have a final well-defined temperature, we find that the efficiency, the closer this temperature is to the initial temperature of the state, the larger the efficiency would be. So the global maximum would be obtained in this limit, where the final state of the cold bath is essentially unchanged. So of course, it's also important to note that the quasistatic limit is not the unique limit where Carnot efficiency can be achieved. However, for any fixed amount of delta C, this maximization that this state achieves is a unique maximum. So one can see that this limit is arguably one of the most advantageous limit that you can do in terms of work extraction. Also, one thing to note is that if you think about the case where the cold bath is a single qubit, then essentially there's only one parameter, which is, well, the ground state probability and the excited state. So this limit would also be the unique limit in order to approach the initial state of the cold bath. So a few more things. Right. So later on, we will be constantly working with this notion of quasistatic limit. But let's now try to relax our assumption a little on the amount of work that we extract. So what happens if I say that I don't require a perfect amount of work to be extracted, but I allow some failure probability? And the first thing that you would see is that, well, there will be some entropy increase in the battery, and you can understand this as energy not being stored as work, but also as heat. One example to see this is that if you start off again in the pure energy eigenstate, with probability 1 minus epsilon, you reach your desired target state. However, for probability epsilon, you fail and you don't know what the state is. This is an example. So we are concerned with near perfect work, which means that the increase in the entropy is arbitrarily small compared to the amount of extracted work. And the formal definition of this would involve a infinite sequence of heat engines, and you say that this sequence of heat engine protocols will lead to near perfect work extraction if and only if, for any positive constant p, you have a non-trivial subset of protocols which will give you that the ratio between entropy and work extracted is smaller than this quantity. So again, if we apply just the standard free energy to analyze this problem, then we have an expression on the amount of work extracted, and Carnot's, we recover basically everything that we have seen in the perfect work extraction case. That maximum efficiency is still Carnot efficiency, still achieved at the quasistatic limit, etc. So now the question is, how well does it perform if all the collective constraints of the generalized second laws also come into place? And so the first thing that we will see is the work that we extract will now no longer be just the difference between two free energies, but it will be an infimum over all the generalized free energy differences, which will essentially boil down to the relative friendly entropies difference. And if you require perfect work, one of the kind of things that I find very remarkable is that you immediately realize that perfect work is not possible in this model because of one of the constraints, which is the D0 relative entropy. And this may seem kind of counterintuitive at first, but I think it has a very nice interpretation or analog that you see in data compression. So in data compression, what happens is, let's say that you have n bits of information and you want to send them across a channel, which might be expensive. So you want to use as least copies of your channel as possible. Now, if your data is constructed or sampled from a distribution which is maybe highly biased, then what you can do is you can compress the amount of bits that you actually send across. You don't need to send the full n bits, but then at the end you do some recovery process, and then with very high probability you will get back the data that you initially intended to transmit. Now, however, there are cases where you really want to tolerate zero error at the end of your recovery process. So in these cases, we know that if you already start off by sampling from a probability distribution which is full rank, then it's going to be impossible to do any kind of compression, and you will have to send the full set of your data across. So essentially, it's the mathematics from here is the same, because you are starting out in an initial cold bath, which is thermal, and therefore has full rank. So near perfect work doesn't really maybe too ideal. Let's use near perfect work instead. And then indeed we see that if you substitute near perfect work into this situation, then okay, you get that Carnot efficiency is going to be an upper bound, which is not surprising given that the generalized second laws also include the usual second law. What's maybe nice to see is that, well, Carnot efficiency can sometimes be achieved. So to do so, we kind of analyze the quasistatic limit, where for near perfect work, then you have to kind of parameterize this failure probability according to your quasistatic parameter, and then take the limit where this quasistatic parameter goes to zero. So this can be achieved in certain cases, but something new also pops up, namely that the achievability of Carnot efficiency now can, in principle, depend on the cold bath Hamiltonian. So we fleshed out the conditions. For the case where you have a coal bath that has n non-interacting qubits. And let's look at this condition for a little bit. Let's denote the smallest energy gap in this coal bath as E min. And with that E min, you define this function omega. So we find a clear separation between what happens to the quasistatic efficiency. So for the case where omega is smaller or equal than 1, then the Carnot efficiency is obtainable in this limit. And this is true even if the coal bath consists of one single qubit. I want to stop here a little bit and kind of appreciate the fact that what we have here shouldn't be taken for granted, because you are actually having the full weight of the full family of generalized free energies determining the amount of work that you produce here, and you only have one qubit coal bath, since it's very different from the usual heat engines that you see. Nevertheless, you achieve Carnot efficiency. However, if omega is greater than 1, then the efficiency of this quasistatic heat engine would be strictly less than the Carnot efficiency. And for the case of single qubit coal bath, we know that this is going to be the unique limit towards the coal bath state not changing at all. So it's for the single qubit coal bath, Carnot efficiency cannot be achieved at all, at ever, whenever this condition is met. So why? Of course, on the first glance, one would say that, oh, this is because you have a full set of second laws and they are more stringent and they show up in the heat engine analysis. Now, we have to check a few things, of course. First of all, we have to check already by using the same framework and only assuming the standard free energy, can you really recover the full power of Carnot's result? And the answer is yes. Of course, one would maybe question a bit on whether the heat engine setting is general enough. And you've seen the assumptions that we made before. In fact, we have kind of played with this a bit more and find that it can be slightly further relaxed, where if you want to achieve Carnot efficiency in this quasistatic limit, then allowing correlations with between the machine and the coal bath and the weight actually doesn't really help. And this is because if you want to achieve Carnot efficiency in this limit, then the correlations between the machine and the rest of the states would have to vanish, but they also have to vanish quickly enough with respect to the quasistatic parameter. And that would kind of hinder the effect on, it will retain the effect of the generalized free energies in this limit. How much? No.
6 minutes.
Okay. So the last maybe question that a lot of people have posed to me, no surprise, is that whether I've quantified work correctly. Is this near perfect work too stringent, such that you have this artifact of Bath Hamiltonian dependence in the maximum efficiency that you achieve? And to answer this question, we actually look at the case where you are interested in extracting what we call imperfect work. And essentially that means that the amount of entropy that you incur on the battery is comparable to the amount of energy increase. So we look at we basically look at an example of imperfect work, and we show that when this is the case, then what happens is that you can even surpass Carnot efficiency. So this is, maybe I will skip this slide. But basically, in this example, what we can do is that we can evaluate the efficiency where we take a particular relation between the failure probability and the quasistatic parameter. And this would give you imperfect work. And we try to, again, look at the quasistatic limit of this heat engine. And when one evaluates this, one sees that the achievable efficiency is actually larger than Carnot. But note that we have only maybe used 1 qubit as the cold bus. We have no additional quantum resources such as entanglement or coherence. So this kind of violates our understanding of classical thermodynamics. And the conclusion is therefore an inadequate definition of work must have somehow be used in this picture. So this is for near perfect work, where we see that Carnot efficiency still remains as the theoretical minimum, but the achievability is going to be bus dependent. So this is one instance of imperfect work where we have found examples of exceeding Carnot efficiency. This is a bit of a curious case, which I will, for time purposes, skip for today. But maybe this one. You decide for yourself, because there's no consensus. Okay, so conclusions. We've looked at how a heat engine can be modeled with this resource theory framework. We have tried to characterize work in different categories, and we have looked at what corresponding maximum efficiency will happen. We've seen that for perfect work, this heat engine will never extract any amount of work. But for arbitrarily good near perfect work, then we can sometimes achieve Carnot efficiency, but there's some dependence on the bar Hamiltonian. For imperfect work or heat-like work, one can even surpass Carnot efficiency. So again, strengthens or reinforces the message that it's very important to first say what your definition of work is, because in most of the case-by-case heat engine analysis that is currently today in the community, people fall into the trap of designing a protocol which has imperfect work and then say that, okay, I have achieved Carnot efficiency, so this must be optimal, which it might not be the case. So there's a possibility for future work, because obviously I've only given you the conditions for the bus-dependent conditions for the case of qubits. It would be interesting to generalize this to qubits. Personally, I also think that it would be nice to look at more realistic thermodynamical protocols where maybe efficiency is suboptimal, but you can extract more work per round, so on and so forth. But I will stop here, and thanks for your attention.
Now, this is more of a general question. Is the motivation behind these, behind quantum thermodynamics to find out more about thermodynamics in the micro scale, or is it? Do you have any applications in mind? Are there experimentalists working on it, and if so, what could possible applications?
You mean of the particular framework that I described, or
for example, yeah,
in general? So I haven't thought about what are the realistic scenarios that one could maybe apply these results to yet, but let me say that in general, results in resource theory thermodynamics, are extremely hard to make connections with like experimentalist settings, just because of the very fundamental assumptions that they start out with. For example, time-independent Hamiltonians and unitaries that commute with the free Hamiltonian, which do not actually, the free operations do not actually feed in any like energy into the system. But of course, experimentalists maybe care more about, I have these resources, and how can I use them to demonstrate something interesting? So I think there's, currently I feel that there's a disconnect between the priorities of the resource theory community and the experimental works on quantum thermal, and I think it would be good to eventually connect them too.
So if you restrict your attention to a family of states that are totally ordered.
Sorry?
If you restrict yourself to a family of resource states that are totally ordered, for example, family of all thermal states but at different temperatures, relative, not necessarily the temperature value, or the family of states that are uniform on some part of their state space and zero elsewhere. then thermal majorization just says that there's total
Yes,
order of those states.
basically the conditions where you evaluate
Yeah,
the thermal
because there's a
majorization.
family of curves that are all static.
Right.
So in all those cases, there's a unique monotone, which I can choose arbitrarily. Like as long as it's fine-grained enough, the total order will always be represented by a unique monotone.
Well, if you have this structure, then you mean there's a unique monotone, yes?
Just for
Okay.
distinguishing this particular family of states.
Sure.
And so all of the order alpha Rényi free energies
Mhm.
just are different
Different
descriptions
expressions
of the same
of the-
total order. So I can write them all as functions of one another
Right.
for that class of states. So in those cases, would you get back to the usual Carnot efficiency result?
So, okay. I will rephrase your question and see if I've got it correctly. So you're saying that if we look at specific limits towards the initial state of the cold bath, such that within this limit there is a total order of the value of these states, then for such a limit, would it always be that we achieve Carnot efficiency?
Yeah, except I would have thought of it as a restriction rather than a limit. That I'm saying. Just suppose you're never going to prepare a resource state on the cold bath that was outside of this special family, which was totally ordered. So my question has changed. I just
Right.
want to, can I reach Carnot efficiency for those kinds of resources?
I would say no, because if you think about the quasistatic limit, it is precisely one of these limits. Because so when we look at the quasistatic limit, we have the cold bath, and the quasistatic limit is basically temperatures which are slightly higher than the cold bath, but there's still a well-defined temperature. For those states, for such a family of states, the ordering in the thermal majorization curve is going to be the same. However, in such a limit, Carnot efficiency cannot be achieved sometimes.
Can you go back to the slide with the quasi-static limit? Because it sounded when you were describing it as not a constraint on the initial state of your resource, but rather a constraint on the kinds of final states that it might get to. Maybe I misunderstood. Was it also a constraint on the form of the initial state?
Hang on, this one, right?
So yeah, it says final state of cold bath is thermal. So how does that correspond to a restriction on the initial state of the cold bath?
No. So maybe I misunderstood. So the initial state of the cold bath is fixed.
Right.
It has some temperature, and I want to say, well, can I find the maximum efficiency? And what I find is that if I take this particular limit, where the final state, where the final state of the cold bath has a well-defined temperature, and this in the limit where this final temperature goes to its initial state, namely basically no change, in the limit where the temperature doesn't change, this is basically how quasistatic limit is defined.
So if that's the case, then I think my question doesn't really match on to this quasi-static limit. I mean, am I right in assuming that the cold bath was the resource, right? The
cold bath was the resource.
Thermal majorization
Right.
curve is relevant and so forth. Now,
Right.
you seem to suggest a moment ago that we assume the cold bath starts in a thermal state at some temperature.
Right.
Now, if I just didn't ask about catalysis, but just about deterministic state conversion, if you told me that it starts in a thermal state, well, then I know the thermal majorization curve is not going to be arbitrary. It's going to be one for a thermal state,
Sure.
and it's going to be a total order. So all those extra conditions it's always going to be total order if you presume that the cold bath starts in a thermal state.
Right. But
So you're saying, therefore, that these what I don't understand is, given that all these order alpha Rényi free energies are just functions of the usual free energy when we have a total order, how can the Carnot efficiency change? I mean, yeah, I just would have expected it when you have a total order that
Okay.
things are going to look like the standard case. And I'm not understanding why that's not true.
The other systems, right? So not just the system, the code.
Could you speak up?
So presumably these alpha free energy conditions will be applied to the full setup.
Put to the full
It's
setup.
a cold path, but then the other parts of the setup as well. And then I'm not sure if during the process you only have the total order or whether you go through a sequence of states.
Because there's also the catalyst and then there's also the
Yes.
weight. So it's maybe not.
So it's the same initial state of the catalyst, the same initial state of the weight. If all my resource states I'm considering are totally ordered, and I tensor on exactly the same state to all of them, they're still all going to be totally ordered.
Well, but the weight might not be a total ordered. I'm not sure exactly.
It seems to me that the only thing you're varying when you consider different versions of this is the initial state of the full bath. That, that's what can change. So that's what could impact the efficiency. For
Sure.
one initial state of the cold bath, it's yay efficient, and for another initial state, it's this
Sure.
efficient. And given that none of the initial states of none of the other systems are changing, if the family of states you're considering for the cold bath are totally
Wait,
ordered.
why are the states of the other systems not changing? Only the cold bath state enters into the form of
Right.
the efficiency.
Right. So I think I want to compare the efficiencies between, say, the cold bath being state rho, work system being tau,
Sure.
versus cold bath being sigma, work system being tau. If I started varying the work system and I noticed a difference in efficiency, I couldn't necessarily attribute it to a difference in my resource. So I have to hold the initial states of the work system constant if I want to pin changes of efficiency on the resource constituting the cold bath, right?
True. I still don't see why this is a problem because given we know that for different states, if I want to extract work out of it, just talking about work extraction, then single-shot work extraction will also be just a function of these the state of the cold bath. Let's say the maximum work extracted, and that's going to be it's not. It's also like, for example, in that case, it would be the F0, which would give the maximum extractable work in the framework of catalytic sum operations. I don't see why there would be. There might be a unique one, but it doesn't necessarily have to be the alpha one quantity.
There isn't necessarily a problem here. There's just confusion on my part that
Right.
the narrative of your talk made me think that the lack of total order, the fact that we've moved to the case of catalysis, wherein we have this whole family of monotones that are needed to determine the order, hence it's a partial order, was key for getting this difference to the Carnot efficiency relative to what we might have expected. But given that you've now told me that, well, we're constraining ourselves to a family of initial states that are totally ordered, I'm now left thinking, oh no, that wasn't key. That it doesn't matter that it's a partial order, that this result follows just from the fact that we're talking about single shot work, not from the lack of total
Right.
order.
I think I'm beginning to understand your question. But only the initial states form a total order, but the final states don't. And you are again maximizing over all possible final states that you can achieve, and the goal is to maximize efficiency. So this is maybe a more convoluted problem.
And then maybe
We can perhaps move on to another question, right?
Thank you. This was really interesting. I want to understand it better. I want to understand a bit better this business of exceeding the Carnot efficiency. So tell me, what particularly I want to know is why Carnot's original argument that you couldn't exceed Carnot efficiency doesn't apply to this case. So, for the benefit of other people, the original argument was, well, we've got a reversible engine that has the Carnot efficiency, and if we had some engine that exceeded the Carnot efficiency, we could run that reversible engine backwards and have something that has no other effect except to move heat from a cold to a hot reservoir without net expenditure of work, which, as David pointed out, if I could do that, I'd be a billionaire. Now, is the answer that, well, what you're doing actually, it's not true, it doesn't have any, when you run this super Carnot engine, it's not true that it's only raising a weight, it's also having the effect of increasing the entropy of the weight or the battery.
Yes.
Is that the key to it?
Yes. A more concrete way to see it is that if you look at the mean energy of the battery, this is increasing. And usually this is how people quantify work, to just say that this is the mean energy difference is going to be my work.
Right.
However, the free energy of the battery is actually decreasing in this process.
Okay.
So the usability of this battery is not really increasing. And this is because of the contribution of heat coming into the
So if I
picture.
use the analogy of a weight, I might, if I'm raising the energy of the weight, I might naively think that what I'm doing is just raising it up, but I'm actually, part of the energy going to the weight is actually just heating it up rather than raising it up.
Yeah.
Okay, I understand. Great.
Marcus?
Okay, so thanks for the great talk. I have more, say, a technical question on this definition of imperfect work. So maybe you can go back and slide. So I think it's really nice once you do exactly something like that. I just wonder about the status of what's really, what is actually done here, because you say, well, I want the ratio of delta S and W to be small. But delta S is basically delta S1 among the S alphas.
Yes.
Now, if you look at S0, for example,
Sure.
then this won't hold.
Yes,
because
indeed.
this will be the rank.
Indeed.
Ask me how many zeros eigenvalues to have, and so this will not satisfy inequality.
Yes.
And I wonder maybe two things. First, what about the other S alphas? So, if this is true, does it also mean that the other delta S alphas are small? And if not,
No.
maybe it's a subtlety here about what we really mean by close to pure or something.
Yeah. So as one can see, like in the example that I provided, you have some probability epsilon that the state is completely junk, and this can be a full rank state for all that matters. So the S0 would be, the difference in S0 would be very great. I guess the reason one picks delta S here is that essentially you have to pick one. Right. And I guess it also relates a bit to free energy. So in the sense that if delta S is much smaller than this extractable work, then what happens is the amount of difference in the free energy is essentially the amount of difference in this work. So
that seems perfectly reasonable. I wonder just if that indirectly smuggles in some kind of standard entropy behavior.
Perhaps.
Which has to do with the Carnot efficiency directly, but I don't know. And I wouldn't know how to do it better or differently.
Yeah.
I was just wondering.
Right. Yeah. I guess one could require that all of the S alpha differences are collectively small in terms of this ratio, but I'm not sure what will happen in that case.
So to follow up on that, I mean, could you instead use like just straight Rennie alphas? Could you use like epsilon smooth variance? Use like epsilon smoothing of the entropies. Because in that case, if the epsilon for smoothing is greater than this epsilon, then S0 will actually be fine in that case because I can smooth that all away.
problem is what justifies this
The
smoothing.
smoothing, yeah.
I guess that's the
But
problem.
it's a question of what imperfections you want here. Is if I find making imperfect work, I find an imperfect entropy as well.
Mhm. I'm not sure.
I'm afraid we have to end there. Time for a coffee break. Thank you very much.
Thank you.